engineers are tasked with stress testing an automated AI workforce, they are placing immense continuous pressure on a complex technical system. There is a hidden financial reality to this development phase. Every single time a testing agent pings a live endpoint, it costs money. Run a continuous integration loop to evaluate those agents using live data, and those fractional pennies rapidly compound into a massive resource drain. Furthermore, real-world data is inherently messy. Relying on live repositories introduces unpredictable variables that skew analytical baselines. Hitting those external servers repeatedly also triggers aggressive rate limits, instantly freezing your development progress. This creates a severe engineering bottleneck. System administrators need to hammer their architecture thousands of times a day to ensure it holds up. But executing that volume on live servers guarantees you will either exhaust your compute budget or get permanently blocked by the host. Engineers bypass this by pointing the pipeline away from functional data and aiming it at a mock environment containing fake data specifically engineered to break. At scale, a well-built AI workforce can easily handle internal bugs. What it cannot survive is the staggering operational drag and unpredictable cost of testing in a live environment. To evaluate the architecture's true resilience, we have to deliberately steer the automated pipeline into a void. Instead of a valid repository, we feed the system a GitHub 404 URL. The pipeline hurtles toward a dead end. Normally, this shatters the process, but this decoupled architecture anticipates the void, catching the error safely and instantly triggering an automated fallback protocol. When an orchestration pipeline survives a hard stop without manual intervention, it proves that a graceful failure is a precisely engineered safety net. Once that fallback protocol engages, the system immediately pivots. It generates structured, anti-slop placeholder text, bypassing the live AI to simulate a deep review without external processing. Next, initiates a 6-phase lifecycle. First, it builds isolated directories without external prompts. Then, it mimics a developer, executing complex CLI instructions within a closed sandbox. A manifest system funnels these outputs into a central ledger, completing orchestration without processing any live code. An automated framework doesn't need to read an authentic codebase to demonstrate that its internal logic executes flawlessly. There is an inherent irony to watching this 6-phase run execute perfectly. The final product it generates is entirely useless. Because the original input was a 404 page, the resulting directories hold no real source code. Outside of this highly specific stress test, the mock reports provide zero real-world utility. Yet, that total lack of real-world utility is exactly what makes the mock repository a priceless tool for pipeline developers. By absorbing a deliberate dead end, safely generating its own placeholders, and strictly organizing its manifests, the testbed validates the system's core logic. It confirms that the routing and directory management work as intended, allowing engineers to deploy live AI agents into a verified environment. If you found this overview of pipeline testing helpful, subscribe to the channel for more deep dives into AI engineering architectures.